Hello everyone, good morning. I am Dr. Farhan Ahmad and today I am going to discuss the topic on media ingredient and formulation for fermentation process. This topic is vital for understanding how to optimize microbial growth and product formation in both laboratory and industrial process. Fermentation media are critical for optimizing microbial growth and product formation in laboratory and industrial processes. Efficient media design enhances yield, reduces costs, and supports scalability. To achieve efficient large-scale fermentation, the media must meet several key criteria such as maximum yield of product or biomass, with maximum rate of formation, minimum yield of undesired products. Beside these, availability should be throughout the year coupled with ease method sterilization, aeration, and agitation. The formulation of fermentation media is a critical step in designing successful experiments and industrial processes. A well-designed medium must fulfill the nutritional needs for microbial growth and metabolite production, provide an adequate energy source for biosynthetic activities. Carbon requirement for biomass production under aerobic condition can be calculated from yield coefficient, Y. Fermentation media serve two primary purposes: to fulfill the nutritional needs of microorganisms and to meet the technical objectives of the fermentation process. The right media formulation promotes the synthesis of either cell biomass or specific target metabolites, depending on the goal of the process. Water, which is a critical component in most fermentation processes, except solid-state fermentation. Water plays a dual role, as a major ingredient in the medium and for supporting operations like sterilization, heating, cooling, cleaning, and rinsing. Next component is carbon, which are most critical component of fermentation media, serving as the primary building blocks for microbial biosynthesis, including reproduction, product formation, and cell maintenance. In most fermentations, carbon sources also act as the major energy providers. The choice of carbon source is critical to fermentation success. Factors such as metabolic efficiency, substrate purity, preparation methods, and regulations must be considered. Careful selection ensures optimal microbial growth, cost-effectiveness, and high-quality product yield. The commonly used carbon sources are molasses, malted barley, starch and dextrins, sulfite-waste liquor, enalkins, oils, and fats. Next component is nitrogen sources. Nitrogen is essential for microbial growth and metabolism, with industrial microbes utilizing both inorganic and organic nitrogen sources. Common inorganic sources include ammonium salts, example, ammonium sulfate, diammonium hydrogen phosphate, and ammonia, which can also regulate pH during fermentation. Organic sources include amino acids, proteins, urea, and various nitrogen-rich materials like corn steep liquor and yeast extracts. The choice of nitrogen source depends on its impact on enzyme activity, metabolite production, downstream processing, and microbial efficiency. The common organic sources include amino acids, proteins, urea, and various nitrogen-rich materials like corn steep liquor and yeast extracts. Minerals play a vital role in microbial growth and metabolism. Essential minerals include magnesium, phosphorus, potassium, sulfur, calcium, and chlorine. These are often added to the media to meet microbial requirements. Trace elements such as cobalt, copper, iron, manganese, and zinc are usually present as impurities in water or other media ingredients, eliminating the need for separate supplementation. Chelators are critical for maintaining media stability during sterilization. Without them, precipitation of metal ions can occur during autoclaving, which affects the medium's composition. Chelating agents like EDTA, citric acid, and polyphosphates bind with these ions, forming complexes that microorganisms can gradually utilize. Vitamins and growth factors are essential for microorganisms that cannot synthesize all cell components on their own. Vitamins like biotin, along with specific amino acids, fatty acids, or sterols, are common growth factors. For instance, in the production of glutamic acid, carefully controlled amounts of biotin are required to regulate microbial metabolism. Precursors are substances added during fermentation to enhance product yield or quality, often incorporated directly into the final product. For example, phenylacetic acid acts as a precursor for penicillin G production. Inducers and elicitors are compounds that trigger product formation, especially in enzyme production. For instance, starch or dextrins serve as inducers for amylase synthesis. Oxygen plays a critical role in growth and metabolite production. Rapidly metabolized substrates, like sugars, can create oxygen limitations due to high demand. Medium components affect viscosity, impacting aeration and agitation efficiency. Additionally, antifoams, as surface-active agents, can reduce oxygen transfer rates, further influencing oxygen availability. Antifoams reduce surface tension and disrupt foam, which forms due to denatured proteins at the air-broth interface. Foaming can lead to cell removal, reduced fermenter volume, lower mass and heat transfer, and contamination risks, affecting sterile operations and product yield. These are ideal feature for an ideal characteristic for antifoam agent. Antifoams mitigate these issues by breaking foam and maintaining process efficiency. The commonly used antifoam are alcohols, stearyl and octyl decanol, esters, silicones, sulfonates. Thank you, everyone, for listening to the lecture. If you have any questions, feel free to compile them. This concludes the presentation. Thank you for watching the video lecture.